So this week we will be going over mass to mole ratios, empirical formulas, as well as molarity and dilution. And so that's going to be the main, yeah, thank you. It's finally good. Yeah, so that's going to be the main topics for this week. And I believe you guys have a test next week. So hopefully you all are prepared and this helps you for these concepts for on the test. Yeah, so let's get started. So we will be going over the first question in the end of chapter 3. It's going to be 18D. If we don't get through all of these questions, that's okay, but I'm focusing on the main ones for this week. That will be the most important. Okay, so we have 18D, and this question says determine the number of moles of the compound and determine the number of moles of each type of atom in each of the following. So when we have a problem like this, we always start with how much we have of it, and then we look at the type of compound that we have. So in this compound we have aluminum sulfate, and so we have, I believe, 3 different species. So we have aluminum, we have sulfur, or sorry, silicon, or I believe that is sulfur. Yeah, sorry, sulfur. Sulfur, as well as oxygen. So in this compound we have 3 different species, or 3 different atoms. So we want to look at the ratio of how much we have of each atom in this compound. So in this compound we have 2, let's go to here, 2 aluminum right there. So we have a 2-to-1 ratio for the aluminum. And for the sulfate here, we have 3 times each one of the amount of atoms in sulfate. So we have 3 times the number of sulfur. So that's going to be a 3-to-1 ratio. And since in sulfur, if hopefully you can see that pretty well, in the sulfur we have 4 oxygen, but we have 3 of the sulfate. So we times 3 and 4 together, and then we have 12 oxygen in this total compound. So that is a 12-to-1 ratio. So now that we have the ratios of everything, let's start out with how many grams we have. And so we will be doing some unit conversions from grams to, the question is asking for moles. So we have 78.452 grams of aluminum sulfate, and I'm going to put that over 1 just like I did the first week when I went over unit conversion basics. So we will need to go from grams to moles. So in 1 mole, I'm going to put that at the top because that's what we want. We need to figure out the molar mass. So the molar mass of this will go right here because grams of aluminum sulfate need to be canceled out with aluminum sulfate on the bottom here. So let's calculate the molar mass of aluminum sulfate. Okay, so we know the ratios in this compound. We know that there are 2 aluminums, and we know that there are 3 sulfurs, and we know that there are 12 oxygens. So adding up all of the molar masses of 3 of the different atoms will then get us the molar mass of this entire compound. So I already have this down just to save us time for looking up the molar masses on the periodic table that are readily available to you. I can show you real quick if you are a little bit unfamiliar with that. So we have aluminum for one of our atoms, and so if you can see right here, the molar mass number is 26.982. And then for sulfur, we have 32.066. And then for oxygen, we have 15.999. And whatever periodic table that your teacher gives you, that'll be the one that you use, and it might have a different amount of decimal places, so don't worry about that. So for aluminum, we had 26.982. And for sulfur, we had 32.066, and for oxygen, we have 15.999. So adding up all of these and multiplying all these numbers out, we will get a value of 342.15 grams per mole. So now that we have the molar mass of this compound, we can put that into the unit conversion right here. So we have 342.15 grams per 1 mole on the top of aluminum sulfate. So multiplying these out, we will get moles, but the question is asking for, I believe, not only the number of moles, but also the number of atoms, I believe. I think it's asking for also the number of molecules. I think that's what it was asking. So it's not only moles, but it's also asking for a molecule. So it's a simple conversion. So we have grams, and we cancel that out, and now we have moles. And we know that in 1 mole of anything, but in this specific case it is aluminum sulfate, we have 6.022 times 10 to the 23rd molecules. So, since we're working with a compound, when we're using the mole to molecules, the mole to stuff, it's always, if you're working with a compound, it's a mole to molecule, and if you're working with an atom, you're going from mole to atoms. So if that makes sense, it's just about the amount of stuff, because we have a cluster, so it's whatever the cluster is, it's just multiplied by how many ever that is, because mole is basically just a conversion of stuff. So let's multiply all of that out. And so our final answer is going to be 1.3808 times 10 to the 23rd molecules of aluminum sulfate. So that is answering the first question of how many molecules do we have of aluminum sulfate? And now the next question is, how do we find the amount of moles or atoms of each atom in the following? So we looked at the ratios beforehand, right here. So since aluminum has a 2-to-1 ratio, so there's 2 aluminums for 1 compound of the aluminum sulfate, and sulfur has 3-to-1, and oxygen has 12-to-1, we can just multiply this number that we got right here. We can multiply that number by the ratio, and it's a simple way of not doing the whole unit conversion again. So since we have 2 aluminums for every compound of the aluminum sulfate, we just multiply that by 2. So 2 times 1.3808 times 10 to the 23rd. And that will be 2.7612 times 10 to the 23rd atoms of aluminum. And since we have a 3-to-1 ratio for sulfur, we have 3 times 1.3808 times 10 to the 23rd, and that will give us 4.1424 times 10 to the 23rd atoms of sulfur. And similarly for oxygen, 12 times the same thing. I'm just going to parentheses it for now to signify the same number here. Times 12 is 1.6570 times 10 to the 24th atoms of oxygen. So that's this whole problem worked out. So basically, just to recap, you start with how much stuff you have, so how much mass, if that's what the problem gives you, and then you want to do a molar mass ratio from grams to moles, and then if it asks you for molecules or atoms, then you'll use the mole amount equation. So that'll be 1 mole of stuff will be 6.022 times 10 to the 23rd amount of stuff. So those are the unit conversions that you will use on a lot of mass to mole and to molecule and atom ratios. Awesome, so that's 18D. Okay, so the next question that we're working with is 23. So the question is, determine the number of, I'll just read it out. It is tiny bit better when you zoom in a lot. Okay, I'll zoom in a lot. It'll be kind of difficult, but that's okay. Yeah, so the question is, determine the number of atoms and the mass of zirconium, silicon, and oxygen found in 0.3384 mole of zircon silicon oxide, a semi-precious stone. So we're working with this compound here. So since we're working with this amount of stuff of the semi-precious stone, we're going to find the molar mass of each one of these, similarly to what we did in the last problem. So for zircon, we have a molar mass of 91.224, and for silicon, we have a molar mass of 28.086, and we have a molar mass of oxygen for 15.999, and this is all grams per mole. So since the last problem gave us a mass and this time it gave us moles, we're going to do the same thing, but it's just flipped around, so we're starting with moles instead of mass. So it asks us to find the number of atoms of each one of these species. So since zircon and silicon both have a 1-to-1 ratio of this compound, the amount of atoms will be the same because there's one zircon in this compound and one silicon. So because of that, we're going to save that for later, but just know it has the same ratio, so you don't have to do the same thing twice if you already know the ratio of these atoms. So let's start with 0.3384 moles of zircon silicon oxide, and so we have 1 mole of this compound, and so we're going to use a ratio between how many of this compound will have how many of whatever atom we're working with. So with 1 mole of zircon silicon oxide, we have 1 mole of zircon, and so then we're in moles of zircon since these two canceled out, and so now we will do the amount of mole to stuff ratio. So we have 1 mole of zircon, so since we have 1 mole of this, we know that we have 6.022 times 10 to the 23rd atoms, because we're working with an atom here. And so working this whole conversion out, we will get 2.038 times 10 to the 23rd atoms of zircon. And just like I said previously, this is also the same number of silicon because of the 1-to-1 ratio. So this is of zircon and also silicon. So we solved the first one. We know how many atoms that we have of zircon and silicon. Now let's see how many atoms we have of the oxygen molecule. So we'll start with the same amount of stuff, 0.3384 moles of zircon silicon oxide. And so since we have 1 mole of this compound, in this compound we have 4 oxygens. So for 1 mole of this compound, we have 4 moles of oxygen. So since we're in moles of oxygen now, we can do the same thing as we did before. Use the 1 mole of whatever you have to 6.022 times 10 to the 23rd atoms. And so since this is multiplying by 4 and the other one was, it had a 1-to-1 ratio, all we have to do is multiply it by 4 in this problem, and we will get an answer of 8.151 times 10 to the 23rd atoms of oxygen. Hopefully the screen is not blurry at all right now. Okay, so since we have those two worked out, and we have to still find the mass of each atom in this compound. We will just use what we had as before and then multiply it by a different conversion. So I'll show you what that looks like. So we have 0.3384 moles of zircon, silicon oxide. And so we have 1 mole of zircon silicon oxide. And for every 1 mole of zircon silicon oxide, we have 1 mole of silicon. And to figure out the amount of mass that we have, we use the molar mass ratio again. So for every 1 mole of silicon we have also 28.086 grams of silicon. And so that's when we found the molar masses in the very beginning of this. So when we multiply all of this out, hopefully it's not too laggy, we have 9.504 grams of silicon. And so since we found silicon in the same way of using the mole and then molar mass, you do the same thing with silicon, you do the same thing with zircon and also oxygen. So we'll do that right now as well. So we have the same amount of stuff of the compound. But instead we're going to go for oxygen this time. And 1 mole of oxygen, we have 15.99 grams. And that's what we worked at before. And so multiplying that out, that'll give us 21.66 grams of oxygen. And so now let's work on, I believe we have not done zircon. So let's do that now. The same method. So for every 1 mole of the compound, we have 1 mole of zircon. And the molar mass of zircon is, I believe, 91.224 grams of zircon. So that is the molar mass for this one, and when we multiply all of this out, we will get 30.87 grams of zircon. And again, I'm working from chapter 3 of the End of Questions in your OpenStax chemistry book, so if you want to look at any of these questions again to what the question was specifically asking, just let me know. I can put down the link for the chemistry textbook in the chat. Okay, so we completed question 23. So now we're going to move on to question 38. So question 38 is talking about empirical formulas and how you find the empirical formula from the amount of percentage of each different kind of species in your compound. So let's go. Sorry, it'll be a bit blurry just for a second. But trust me, it'll get better. Okay, so we're giving these values of 28.7% potassium, 1.5% hydrogen, 22.8% phosphorus, and 47% oxygen. So we're going to use this equation to figure out just the conversion of percentage to grams, so we're working with a mass. So this equation looks like this. You work with the percentage equal to the amount of grams that you have over 100 grams of the total compound. And we're going to work with atoms, not compounds here. But this percentage here will equal the amount of mass that we have. So if we're given 28.7% of, I believe it's potassium, then we will put a 28.7 gram amount of this compound. We're just assuming, just as a basis for working with percentages, we're going to assume that we have 100 grams of this compound to then convert it, because these grams cancel out, and when we multiply it by 100 we get a percentage, and that'll bring us back to 28.7. So you put 28.7 divided by 100 times 100, and then you get that percentage back. So in the end we're working with 28.7 grams of potassium. And so we're going to do the same thing for the other species in this. So we have 1.5% hydrogen. So that means we have 1.5 grams of hydrogen over 100 grams of the total compound. And so that will give us 1.5. This is not an equal sign, this is just telling you how many grams that we have. So 1.5 grams of hydrogen, and we also have the 22.8% of phosphorus, and you know where this is going. It's the same thing. It's 22.8 grams of phosphorus, and we have 47% of the oxygen, so we'll have 47 grams of oxygen. So these are the values that we're working with. So now that we have a percentage to a mass, we're going to use these masses to then use a molar mass ratio conversion for each one of these different atoms, and then we'll have moles of each. So I'll show you what that looks like. So we have 28.7 grams of potassium here, and we want to get to moles. And so using the molar mass of potassium, we'll put the 39.098 grams of potassium per mole on the top here. And so that will come out to 0.7345 moles of potassium. So now that we're working with moles of potassium, we have to do the same for the rest of the atoms that we have. So we have 1.5 grams of hydrogen, and using the molar mass ratio, we have 1.008 grams of hydrogen for every 1 mole. And so then we'll have 1.4881 moles of hydrogen. And so now that we have moles of hydrogen, let's do the rest. We have 22.8 grams of phosphorus, so that's 30.974 grams of phosphorus for every 1 mole. And again, these are just the molar masses from the periodic table. And so we will get 0.736101 moles of phosphorus. And similarly with oxygen, let's put down its molar mass of oxygen. So then we will get 2.93768 moles of oxygen. So we have all of these values. We have now moles of potassium, moles of hydrogen, moles of phosphorus, and moles of oxygen. So now what we do is we take the least numbered value of all that we have, and we divide each amount of moles by each one of them. So in order to do this, the reason why is we find a common denominator, and just to get rid of all these decimals, we find a common whole number value for all of these atoms. So it looks like the mole number of potassium, the 0.73405 is the least, is the smallest number here. So we're going to divide each one of these values by that common denominator. So what that will look like is 0.7345 moles of potassium divided by the smallest number. We'll just get 1 mole of potassium. And then for the amount of moles of hydrogen, we had the 1.4881 moles of hydrogen divided by the smallest number, which was this one, same one. We'll get 2.027 moles. And so since this is so close to 2, we're going to round to 2. And you'll see that all these numbers will be very, very close to a whole number. And it's not going to be like very specific because there's a lot of decimal places that we're working with. So we're going to round to the wholest, or to the nearest whole number. So the next one is 0.73610 moles of phosphorus divided by that value. And so we will get 1 mole of phosphorus. And finally, the last one, 2.93768 moles of oxygen divided by the least number here, we will get 4 moles of oxygen. So now that we have, I'll just cancel this out right here, make it look a little bit better. Now that we have the amount of moles of potassium, hydrogen, phosphorus, and oxygen in the wholest number ratio, now we can actually write the formula for this compound. And so what this compound looks like is KH2PO4. So we have 4 atoms of the oxygen, or sorry, 4 moles of the oxygen. We have 1 mole of phosphorus, 2 moles of hydrogen, and 1 mole of the potassium. And so that is what that looks like. It's a long process to get to the final ratio, but once you know where to start and where to end, it gets easier each time. So you're always going to start out with the percentage, then to grams, or the mass of whatever you're working with, and then you're going to go to moles, and then use the smallest number for the common denominator to get the whole mole amount for each one of the species that you're working with, or atoms. So that's the process for finding the empirical formula. So we worked with 38, problem 38. Let's move on to problem 44. And so this question is asking what changes and what stays the same when we have 1 liter of sodium chloride, NaCl, when it's diluted to 1.80 liters of solution. So this is a theoretical, or not a theoretical problem, but this is a word problem. No need to calculate anything. But basically, when we have 1 liter of a solution, and then we're diluting it to make a larger volume, what happens is there's going to be the same amount of the sodium chloride, but it's just going to be diluted, so its concentration will be reduced. But it's still there, but the amount of stuff per volume is going to decrease because of this equation right here. You most likely have gone over this in your class. So this is the concentrated molarity, concentrated volume, and this is the diluted molarity and the diluted volume. And as the volume goes up in the dilution amount, the concentration has to go down. And so that's why that happens, because of this equation here. Okay, so let's move on from 44 to 48. And so 48 is asking us to find the molarity in each of these solutions. So for 48A, we have 1.457 moles of potassium chloride. I'll write this right here. And 1.500 liters of solution. Just get rid of this really quickly. Okay, so since we're starting out with this amount, we have moles of a solute and we have amount of liters of the solution. So this amount of 1.457 moles is already in the solution, and so since we're working with moles of solute and we know the amount of liter of solution of the total amount of everything, that's the definition of molarity. So we will divide both of these by each other. So we have 1.457 moles of KCl, and we have 1.500 liters of solution. And so dividing this out, we will get 0.9713 moles of solute over liters of solution. So that is the molarity for this given amount of potassium chloride. So let's move on to another problem of 48. This is 48b, and this has 0.515 grams of H2SO4 hydrogen sulfate and 1 liter of solution. So that is the question. it's also right here. Because we have the amount of mass of the solute and we have the amount of total solution, we will divide both of these to find the molarity. So the molarity equals 0.515 grams over 1 liter, and so that'll give us the same number back, and so we will have 0.51 molarity for this problem. So it also asks us how many, I believe it also asks us the moles per liter of not only the hydrogen sulfate but also of each mole. I'm going over my notes here. Okay, so scratch what I just said. This is how you actually solve it. So we have the molar mass of hydrogen sulfate, and so we have 2 of the 1.008, and so this is hydrogen molar mass, and then we also have 4 of the oxygen, 15.999, so that is the molar mass of oxygen, and then we have 32.066. And so the reason why we do this is because we have to find out how many grams we actually have of this. So we have the amount of grams of the hydrogen sulfate, but we don't have the number of moles. So when I divided it by the total amount of solution, you have to work with moles on the top, and I was just confusing grams and moles. So we have to convert the amount of grams here to moles, and that's why we use the molar masses, just have we have done before. So we have 32.066, and that is the sulfur molar mass, and so adding up all of these, we have 98.078 grams per mole. So since we have the 0.515 grams of H2SO4, we're going to use that molar mass, and we have 98.078 grams per 1 mole of H2SO4. And so we have 0.00525 moles of H2SO4. And so that's the amount of moles that we have from the amount of mass that we're given. And so we're going to use this number of moles to then divide by the amount of total solution that we have. And so we have 1 liter of solution, and it makes this division problem very, very simple. Let's just divide by 1. So we will have a molarity of 0.00525 molarity. So that answers that problem. Let me know if any of this is confusing to you. I can slow it down or explain it in another way that makes more sense to you as well. Okay, so let's move on to the next question. And so this question is going to be question 50. And so it asks, I'll just read it out since you won't be able to read it too well. Don't worry if you can't really see it on the screen. So the question asks, consider this question. What is the mass of solute in 200 liters of a 1.556 molarity solution of potassium bromide? So we're working with a mass of a solute and also a concentration of this solution. So what we have to do, the question is asking us is how do we solve this, break it down step by step, and then actually answer it. So what we're going to start with this is the actual moles per liter, and so that's the molarity. So we're going to start with the molarity that we have, and then times it by how many liters of solution that we have, and so that will give us moles of solute. So when we multiply these, it will give us moles of solute. And then once we have moles of solute, then we can use the molar mass. of the KBr to isolate the mass that we have, because when we are working with a moles of a compound or an atom, and we're multiplying it by the molar mass of whatever same thing we are working with, we can isolate either moles or mass, whichever one we're starting with. So if we're starting with moles, we can get to mass. So that is what we're going to do. So we have the molarity given of 1.556 moles of potassium bromide, and then we're going to multiply it for how many liters of solution that we have. So we have 200 liters of the solution, and then, since that's what we know so far, now we're going to multiply it by the molar mass. And so since we have, right here is liter of solution, so these liters of solution get canceled out, so we have moles here. And so we'll put 1 mole of KBr on the bottom. And then we have, sorry, let's see if this is a little bit better to see. We will have a molar mass of 39.98 plus 79.904. That's the molar mass of KBr. And multiplying all of these out, we will get a answer of 37033.4, and this is grams, by the way, of this last one. 0.4224 of grams. And so since we're working with such a large number here, we're going to convert it to kilograms, or you can leave it with grams. Just ask your teacher, whichever they prefer. So if we're working with kilograms, grams to kilograms, there's 1,000 grams in a kilogram. So this would just be this value here. And so since we're working with the molarity that we started with of 1.556, we have 4 significant figures here. So our answer is going to be 4 significant figures. So we have 4 significant figures in this answer. So that is how you get from a molarity and a liter of whatever solution that you have to the mass of what's in the stuff, so the solute. Okay, we worked on problem 50, and so we have 2 more problems to work with, and so the next one will be 56. And let me make this bigger so you can see it better. Okay, we have 2.026 grams of iron chloride in 0.1250 liters of this solution. So this question is asking for the molarity. So since we know that we have 2.026 grams, we want to calculate how many moles we have of that. And so since molarity is moles of solute over liters of the total solution, we have the total amount of solution, so we don't need to do anything to that. So let's first get from grams to moles. So the molar mass that we'll use for this conversion is going to be 55.845 plus 3 times, because we have 3 chlorines in here, of 35.453. And so that's the molar mass of the iron chloride. And so let's start out with how many grams that we had. We have 2.026 grams. And then using that molar mass conversion, I'll just move this down so I don't have to write it again. Grams of iron chloride. And that is for every 1 mole of iron chloride. And so multiplying these out, we will get a value of 0.01249 moles of iron chloride. Awesome. So we have the amount of moles of the iron chloride, and so once we divide by the total amount of solution that we have, then we will get the molarity. So the molarity equals 0.01249 0.0444 moles. I'm just carrying out more decimal places. Divided by the total solution, and that's 0.1250 liters of solution. And so we will get a molarity of 0.09992. Molarity of iron chloride. Okay, so we found the molarity of this problem. This one is a little bit quicker to solve than the other ones, but I think the next one is a little bit more complicated from my understanding. I think so. So this is more of a thinker. So this question is asking us the final concentration of a solution produced when 225.5 milliliters of a 0.09988 molarity solution of sodium carbonate is allowed to evaporate until the solution comes to 45.00 milliliters. So we have the molarity of this concentration, but the volume is going to be reduced, so that's going to change the end concentration. So that's what we're going to answer. So we're going to start out with how much stuff that we have, and then figure out how many moles of this solute is in the original solution. So in the original solution, we have the molarity, and we have 225.5 milliliters of this solution. So we're first going to start out with that to convert to moles. So we have 225.5 milliliters of sodium carbonate, and we want to go from milliliters to liters, so there's 1,000 milliliters in 1 liter. And now that we're in liters, now we can use the concentration. So for every 1 liter, we have a concentration of 0.09988 moles of the sodium carbonate. And so multiplying all of this out, the 225.5 divided by 1,000, getting that answer, and then multiplying by the 0.09988, we will get the amount of moles of 0.02252 moles of sodium carbonate. So now that we have the moles of solute, all we have to do is divide it by the end amount of solution, because the amount of moles that we have of the solute does not change. Only diluting it, or the evaporation, that's only the total volume. So we're going to divide by now the new volume of once it's evaporated a little bit of the 45 milliliters. And so since we have 45 milliliters, let's convert that to liters. And there are 1,000 milliliters for every 1 liter. So now that we're working with 0.045 liters, we will divide these two values. So we're going to divide the amount of moles that we have, because that's not changing, of the Na2SO3 or CO3, divided by 0.045, sorry, it's a 4 not a 9, of solution. And so that will equal the molarity of the sodium carbonate. And it's going to be 0.5004 molarity of the Na2CO3. So as we can see, the original molarity that we worked with was, I believe, the original was 0.099 blah 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 blah. So multiplying or dividing by how much we have of the original concentration to how much we have of the new concentration, it's actually 5 times the amount. So in this problem, 5 times the concentration was increased when it was evaporated. Okay, so that's it for all the questions for today. Let me know if you want me to go over any problems that you're confused over that we went over today, or any that you have on your mind, if you have any at all. And if not, we will end the stream for today. Good luck on everybody's test, and hopefully the concepts are ingrained a little bit more.